Okay, this is the second seminar. So in this one, we have Jérôme Petit. He's a global product manager at Experian. Prior to that, he was a quantitative analyst and also a product manager working on fixed income and foreign exchange products in Finastra, and also a quantitative analyst and statistical arbitrage at Rational Finance. During these different periods, Jérôme was involved in pricing financial instruments using mostly stochastic models and machine learning. And he also has a PhD in quant topology from the University of Montpellier in 2007, and a master's in finance from SEC at EC and CINAM, I hope I got that right, in 2013. So thank you so much, Jérôme, for being here. His talk is going to be focused on quantum machine learning and fraud detection, and I hope that you all like it. Thank you so much, Jérôme. All yours.
Thank you. Can you all hear me well?
Yeah.
Perfect. Thank you. So yeah, I started my career as a researcher in quantum topology, and now I'm back in quantum, but more quantum computing, let's say. So I will present you the work I've done during this master. It's related to the application of quantum machine learning for fraud detection. So this work has been submitted and presented in September under the supervision of Alejandro Borrallo Rentero. I hope I pronounce it well, but in any case, if not, I beg your pardon. So I thank you, the organizer, for inviting me and to give me the opportunity to present this those results. So let's start with the agenda. So during this presentation, I will do a brief introduction on the problem statement, state of art, motivation, a bit the goal of this thesis. I will spend some time on the data because it's key to understand the difference between classical and quantum, and especially what I've done, which data I've used to set up the scene. And then after, I will present you the different methodology techniques I have used, compare and give my conclusion on this work. So the overall idea was to apply quantum machine learning to this fraud detection in banking, in financial institution problem, and see if it brings value or what it brings compared to a classical model, and especially what could be the next step in order to improve the current result. First of all, why fraud detection? There is a massive demand from the industry, bank, financial institution, because the fraud costs more than 3 trillion each year, 3.7. It's a massive loss for the bank and all the financial institutions. So it's a problem, and they want solution on how to improve their fraud detection. And today what we observe is that most of the business are, I would say, slightly confident in the ability to detect fraud. Only 54% of the bank. And what they want to do to improve this confidence, to improve their approach, is mainly focusing on machine learning to improve the fraud detection, to achieve some good KPI or good result, more than 76%. But even though with this machine learning, the level of confidence is low. So there is a trend today to see if quantum, which is in the end quantum machine learning, the use of machine learning technology with quantum computer, even if we are in this kid world, with still noisy quantum computer, we can improve this fraud detection to reduce the cost and the impact for the bank, and to bring more confidence in the model. Furthermore, there is another aspect that is mentioned by Helen early on. Quantum security will become more and more a real problem when the technology will be more production ready and used at scale. But today it's more improving the result by itself and leveraging the quantum and machine learning aspect. Where we are, before going into the work, it took some time before this presentation to check a bit where we are today in the industry research. So lots of publication. As you can see, this one is August, where we go even further than the classical quantum machine learning, unsupervised quantum machine learning, really specific to fraud detection. So they are with some involvement of some researcher working for bank. We see industry partnership. So Rabobank partner with Quantum Computing Inc. in order to improve their fraud detection, again, to provide better service for their client and to reduce the loss on their side. So this partnership starts some months ago, December 2022. And the idea is to leverage quantum computer, quantum technology to improve the fraud detection. And we see other approach from large banks like JP Morgan, HSBC, BNP, where they have inside the bank a quantum program to address fraud detection or to address invest banking, such as pricing of complex or derivative product, portfolio management, and so on. So there are different aspects, partnership or internal development. But as you can see, the industry is ready to accept and work with quantum technology. So let's go back to the work. I've used for my master thesis and for this presentation, I've used transactional data, which come from payments, so terminal payment, online payment. You use your credit card, and this is the flow of your data, which we call sometimes payment processing flow or transactional data. So you go to acquire bank, issue bank, and you capture all this information. Most of them are PII data, so it's difficult to use. That's why I use Kaggle data coming from Kaggle contest that came from European bank. And what they have done is they have cleaned the data in the sense remove all the PII data and already pre-process the data. The main idea of using pre-processing data was really to focus on the machine learning by itself and spend less time on fine-tuning and pre-processing the data to compare directly the quantum machine versus the classical one. So here, this is what we have used. And the second reason of why we use this data is because it's a data already used in other articles, especially one that apply another technique for quantum machine learning that is not using QCT or I would say qubit. In this approach, they use continuous variable. So it's the continuous approach of the quantum machine learning. They use, I think, fork expansion instead of finite dimensional Hilbert space. But we will not cover that during the presentation. So that's the two reasons of why we use this data. This data was highly unbalanced, because this is usually what happens with fraud. You don't have half-half, hopefully. So to do what we have to do is we took the data, we pre-processed the data. This one was done by the data provider, and we undersampled we apply undersampling methodology on it. Why? Is because machine learning algorithm, classical or quantum, was better on balanced data. Otherwise, you will have a bias due to the fact that the data is unbalanced, so they don't consider the minority class as important and only focus on the majority one, which can bring you some bias in the model and issue to at test level. And then after we apply a PCA reduction. The main reason of the PCA reduction was to reduce the number of features and to get the value of quantum machine learning with a reduced number of features, in the sense that can we get better insight with a reduced feature compared to classical machine learning applied to a whole data set? Are you able to obtain pattern that you cannot track with classical one? The second main reason was related to the vanishing gradient issue, so called barren plateau. Once you increase the number of qubits in quantum machine learning, the probability of having vanishing gradient, not due to the fact that you reach a minimum or a maximum local minimum or maximum, is high and cannot be considered as null. So in this case, it's an issue, and we wanted to reduce that to avoid this effect. Those are the two main reasons of applying this PCA for dimensionality reduction. Here is the dataset you obtain after undersampling of the dataset. So we base on the minority case. So we have this data, 984 transaction, balance with 2 features. So this is our tactical approach. What we have done, we have taken the data, we have applied the preprocessing, and then after we apply classical machine learning to create a database. So this one is unprocessed data that we didn't apply PCA reduction. Then after we apply again the classical machine learning on the data after the PCA, after the reduction, to see what happens and see if there is a degradation or not. And then after, this is where the quantum aspect in the data pipeline appears. So I don't know if you can see, because I have this screen on my side. You can see it or not? Yeah, maybe it's better like that. Yeah, okay. Quantum encoding. So for a classical data universe, you stop here. But for quantum machine learning deal with quantum data. Today, the data comes in the classical world. To apply quantum machine learning, you need to map this classical data toward a quantum data. And the technique used is a feature map, because a quantum space is an Hilbert space. So you come from your classical space toward the Hilbert space, and you use a feature map. You have various types of feature map. It can be angle encoding, it can be poly expansion provided by QCT. Most of the package provide their basic feature map to map from classical to quantum. Once you are in the quantum world, you can apply your algorithm, which can be, in this case, quantum SVC, quantum machine learning. And before that, of course, you have to select a simulator. All the work done and presented is based on simulator. So we didn't use a real quantum device. It can be a following work. So those are the 2 additional tasks. And once we have encode, execute the algorithm on a quantum simulator, we are able to obtain a result of this quantum machine algorithm and compare to the classical one. How did we compare? We have used the following metric, which are classical for, I would say, machine learning domain, which are the precision, the recall, the F1 score, and Matthews correlation coefficient. We use the F1 score. The main reason why is because the F1 score is an average of the weighted average, of course, of the precision and the recall, and takes into account true positive and true negative. And here, what we have used too is a confusion matrix. Why it's important is because the confusion matrix allows you to give a quick view on the true positive, true negative, false negative, false positive. What does it mean? Here, for instance, you have a true positive, which is it's a fraud. We detected fraud and the data was fraud. So it means that you have a good classification of the fraud, but a bit less for the true negative, which are not fraud. And here you see the bias and the error based on the false negative or false positive. With this view, you are able to detect if your model classifies well for fraud or not fraud. And especially once we want to generalize. So we apply it on the test. We train using this metric, and then we apply it on the test set to see the level of generalization. Now, classical machine learning. We have used 3 classical algorithms. We use cross-validation with 10 folds in order to optimize and fine-tune the model. We use from the really simplistic one, I would say logistic regression. We are in binary classification. Is fraud or not fraud? This one is well done, well commonly used as a benchmark, or usually as a benchmark. We expect to have always something better than that. The SVC, we use kernel RBF, and then after we apply machine learning multi-layer perceptron using scikit-learn. So we use 300 hidden layer. So those are the setup. Wanted to, and again, the data is pre-processed, and we apply those methods, and this is what we compare to the classical, the quantum machine learning. There are several categories. In our case, we are in the domain of supervised learning because we already know from the train and test which one are fraud and not fraud. And we focus on quantum SVM and quantum machine neural network. Quantum SVM, in short, is we already have the feature space because in SVC, you already map toward a larger space. The quantum aspect comes for the kernel. So the kernel computation here, this is where the quantum aspect comes. You will use quantum computing to compute this kernel and then apply all the other algorithms. So all the feature map and canonical feature map follow the same process. In terms of feature map, we have used poly expansion. And the second use case is quantum neural network. As I said, this one is what we call sometimes variational quantum network to quantum algorithm. It's a mix between classical and quantum in a sense that you mix classical methodology with the input layer and output layer. Then you have a quantum circuit inside, and this is what you use for the quantum technology, quantum machine learning. So you will compute that as using the quantum technology. So you will have some parameter. You will measure it, you obtain a result, and then you apply the gradient on the result. So that's why it's called variational and hybrid quantum network, because it's a mix. It's not fully quantum. And for this one, we use, again, there is a classical layer. So I use softmax for the outbound and for the inbound sigmoid, classical one, and I use a quantum circuit. I will go into detail. The quantum, this is in the quantum circuit where you will have your feature map that will map from the classical work to the quantum work, and I've used angle encoding. So those are the feature encoding I've used. As you can see here, just to explain the results, so it's mainly it's mainly rotation. So you gate. Here you can see the impact on the input 1, 0. And actually the Z feature map is built in the QCT library, and you can add a repetition on it. So this is with 1 repetition, and this is with 2 repetition. As you can see, some feature, some elements are no more represented. The same for the ZZ feature map, where you add an additional C0 gate and U gate. For the hybrid QNN, I am in the Penny Lane framework. I have used angle encoding just to test a different way to map the data, mainly applying Hadamard gate and rotation. And I use poly expansion. I use Z measure on each qubit. So this is what we observe for 1, 0 and 1, 1. So as you can see, the distribution has changed. The last piece of work here, as you can see, this is the encoding, the embedding, so the feature embedding. And then after, this is the circuit I've used. This circuit is called provided strongly entangled layer. The idea is to have a number of parameters. So in this case, as you can see, 6 times 2 times 3, so 36 parameters. And those are the ones that will be computed by the quantum network. And at each iteration, you apply a gradient on it, and you update your parameter to obtain, in the same way as a classical neural network, to obtain a good result. So you define epoch, batch to reduce your cost function. What we have used angle encoding, and we have used this strongly entangled layer, which gives this circuit. And we have used Z measurement for each qubit. In terms of classical layer, I've used a sigmoid activation with a 2 node and a softmax activation for the two node for the output layer. Why? Is because it's the basic one usually used for binary classification. And I wanted to focus the attention on the quantum aspect, so the quantum circuit, to see where there is a value. The sigmoid is allow us to have something center. So those are the results. Go back to the results. So for the whole data set, the multi-layer MLPC gives the best result compared to the classical one. really close to the F1 to the logistic regression. This is what was expected, is more flexible and have more parameter. Then after we work on a reduced data set, the one with balance and a reduced number of features, 2. And in this case, as you can see, the precision multi-layer perceptron still have the advantage. But if we compare to the F1 score, the hybrid QNN gives best result than the multi-layer. I would say slightly better, but at least a bit ahead. So that gives us some interesting results in terms of training. It looks like we can train better. So now the next question is, what will happen on the test side? Just for the quantum SVC, what we have observed is that increasing the number of repetitions, so increasing the complexity, the number of gates of the feature map, does not improve at all the precision. I wouldn't generate that result, but I would say more gate is not a guarantee of better result, at least for this use case. And then once we test on the test data to test the generalization, what we see is that the hybrid QNN are the best behavior, in a sense that the generalization will be the best. So you train better and you have a better generalization on your test data. Again, we're on a reduced world. So training was done on the reduced world. So that's really interesting to see the behavior and the fact that quantum, even with a reduced number of dimensions, you're able to get insight and have a good generalization of this insight. I have some reference at the end of the call related to similar work done by Christophe Père and Javier Mantia on dimension reduction and apply quantum machine learning. So they went further than the PCA. They applied different technology methods such as LDA, and I don't remember the last one, and compare the classical versus the quantum machine learning to see how they behave with a reduced number. And finally, we compare with the full benchmark. So those are the one trained with all the feature, so not with the dimension reduction. So what we see that there are a good generalization with the logistic regression, a bit less for the perceptron. It means that maybe there is some overfitting here. And but as you can see, the hybrid QNN match what we observe with multi-layer perceptron. So we are not that far from the logistic regression. So even if we didn't train on the full feature, on the full data set, only with a reduce, we are able to have a good training result and a good generalization. So that's really something interesting. Again, all has been done on simulator. Default qubit for Penny Lane and QASM for IBM. What it brings for me is that first, I really want to test that on a real device to see how the noise will impact. I'm happy to have these 2 qubits reduction to avoid this barren gradient plateau. And I think I don't think any value for now on increasing the number of qubits can come in a later stage. But I think that the main interesting is maybe how we can fine-tune this this quantum circuit, because really we didn't spend time on the fine-tuning. We took one with a pre-build, see how we can train and which kind of insight we can get with a classical neural network, and see how it behaves with in a noise environment. And I think the other key feature, and I've seen lots of articles that talk about that, is on the feature map, especially related to the quantum SVC, where I think it will bring value to investigate a bit more and on how to improve the choice of the feature map. I've seen that this article, the first one, automatic design of quantum feature map, they use genetic algorithm to put in for a process to define which feature map fits the best. It's only focusing on quantum SVC, but there might be some potential for other model. Again, this result are really interesting. I encourage you to read this article where they use continuous variable quantum neural network. So they use the same data set, but they use a different approach than the classical quantum machine learning. They evolve in the continuous variable, use penny lane framework, and obtain really good result on the same data set. I think they reach 0.97 in terms of precision on the test data. That's all for me.
Thank you so much, Jerome. It's an amazing presentation. Also, it's a case that I think could have a great impact. In the end, as you mentioned in the beginning, the amount of money that is lost in fraud is amazing. So any minor improvement in that is going to have a huge impact. Do you have any, well, I don't know if there's any questions from anyone. Feel free to jump in, open the microphone, or just drop them in the chat. I see one hand raised. I don't know from whom, but yeah, Juan, I think it's you, right?
No?
Hello.
Hi, Jerome.
Hi.
Yeah, I have one question. I saw that you used the PCA to do a dimensionality reduction of your data set to mostly 2 variables. I was wondering what was the reasoning behind using only 2 variables, and would you be able to obtain better results if you used more dimensions in the data set?
That's a good question. So I mainly focus on PCA due to the article I mentioned with Christophe Père on the kind of test different model. Why only 2? There was some, I would say, yeah, I could have tested 3, honestly. Mainly time, I would say, and I wanted to avoid any impact of gradient barren gradient plateau. So I wanted to avoid this vanishing gradient. So that's why we focus on 2. And the idea was to expand the scope to 3. I don't expect, I'm not sure, because as you can see, look, for me, there is no direct correlation. What I've observed is that once you increase the complexity of your feature map, so the number of gates, you definitely don't have good results, better result, at least for quantum SVC. So it's not even an overfitting problem. It's just the training is not good. So that's why I stick to 2. But yeah, it can be a good next step to see how it behaves. Maybe better result for hybrid QNN.
Thanks. I think you've answered my question.
Yeah.
Yeah.
Any other questions from anyone?
Hello.
Yeah.
Hello.
Yes, Jérôme, thank you
Hi.
for your presentation. I have 2 questions. The first is, how do you determine that the angle encoding was the best for you? Did you test different encoding?
Yeah, I test different encoding. Again, yeah, I wouldn't say the best because, and this is, I think, an important, I would say, axis of improvement. Today, I cannot answer this is the best for this use case. I've tested several because the choice is really large, and based on the panel I've chosen, yeah, this was the best result, or at least the other didn't bring that much value. But I think it could be key to have some process, protocol, or I would say high-level result to say, okay, like as I said, automatic feature map detection that allows you to be sure that this is the best. You have to think that it's there is 2 pieces. There is angle encoding, so feature map encoding, and then after you have your quantum circuit. So I would say I should have put in place a cross validation. Ideally, this is the best, but I don't know yet. I don't know today how to put that in place to go through all the possible encoding and all the possible circuit. I don't know if that answers your question, but
yes, it's okay. And another related generalization. Did you use another another data set, or I didn't understand how do you determine the
No, I use the
generalization
same.
of your model?
I use the same data set. I just split in train and test. So I think this is where I apply. So yeah. So I split in train. I apply this ratio to split the train and test.
Okay, you use the test, but you didn't use another for validation, an external data set for.
I use for the classical machine learning. I split in train, validation, and test. So actually, you train in the subset, you validate for the cross validation on your validation set, and the test. But it all come from the same test, and I use scikit-learn library to do the split. But I didn't cross validate with another data.
Okay.
Yeah.
Thanks.
Just keep in mind that the data set came from Kaggle as
Yeah.
credit card, and actually it's already pre-processed, so was
Yeah.
difficult to mimic
Find
with
another.
Yeah. Because here you have all the PII data they have to remove. They already process with internal tooling. I would say it was difficult to replicate with another one.
Okay, thank you.
You're welcome.
I had one quick question. So, Jérôme, you intend to continue working on this? Do you have any next steps or any plans?
Would love to have more time to work on that, but not that what blocks me today is more the time, honestly. But I would love to, and that's what one of the reasons of this seminar. Too, if someone is happy to work with me on that, yeah, I would love to work on that. Initially, it was maybe. So again, I'm not talking in the name of Experian, and I do not represent the idea of Experian, but I see some interest. I see some market activity on that. The next question is we have to prove that is better than classical machine learning. Otherwise, nobody will use that. That's the first point. More robust, more stable. And yeah, I think I would love to work on that. So happy to engage in any partnership or collaboration to write this paper and achieve some next step.
That's great. Okay, I don't know if do we have any other questions? Okay, I think we are done for now. Thank you so much, Jérôme, for being here and for sharing your experience. So we are going to have a small break again until, let's say, we can meet again in 12 minutes. So we're going to stick to the schedule. Thank you all so much, and see you there. Thank you.
Thank you. Thank you for the invitation. Thank you.